All right, so this is going to be interesting doing a recording of this class because I just realized now that I forgot to upload the video from this morning's class, Math 285. So I should have enough disk space for this recording because the trouble is, however big it is, you need twice as much for the actual saving of it. So hopefully, what? Well, so the way it is now, I have like 11 gigs available, hard disk space. A recording of this class takes about 3 gig, or maybe 2 point something gig. So it should be okay, but we'll see because I have like 5 gig from this morning's class. It's taking up space, and I just tried to copy it onto my flash drive, and I don't know if you were watching, but it would not let me. So not sure what was going on there. So we'll just see how it goes. Now, first, the announcement side of things, a few items for you. Okay, so for those of you who actually submitted homework 1, which is thankfully most of you, has been graded. See grade and comments in the Canvas gradebook. You should have gotten some sort of notification, like an email notification or something from Canvas, depending on how you have your notifications set up, that there is a grade. So for all the actual info about it, go to Canvas. I think there were a couple people who had not turned it in, so please rectify that. So as not to fall further behind. But all in all, they were quite good shape. It's kind of surprising. Most of the point deductions were on the very first problem about the diagonal system. I would not have expected that. So, okay. Now, item number 2. About the midterm. So a practice has been posted on the lectures page with a solution. So we go over there to the site. Okay. All right. So on the entry for the date of the test, February 26th, so you can see the practice test here. Now, the way it's going to work, and those of you who just took 460 last semester will be familiar with this format, there's going to be 2 parts to it. One of regular problems, and there will be 5 of those. 5? Yes, 5 of those. And there will be a formula sheet. I might add to this. I haven't really decided yet. Now, how to carry out certain algorithms, which is part of homework 2, like carrying out Gauss elimination or LU decomposition or pivoting. That's something that you should know how to go through the motions of, as opposed to like having a written description of the algorithm and carrying it out. This is something that's going to come up from the next section, 3.4. So I might add to this as to what sort of things you'll have here. I just haven't decided about that. So that's the only thing that's in flux. Okay, so how a midterm breaks down. Okay, so 5 regular problems, and just to give a quick overview of what I mean by that. For example, okay, problem involving using Gauss elimination or partial pivoting. So how you would carry that out to solve the system. I'm sorry, the chatter is incredibly distracting. So, okay. Okay. I'm reminded of what my calculus professor he would say. He would say, "Would it be possible to stop the gibberish?" So, his exact words. So, okay. Okay. And so carrying out the algorithm of Gauss elimination back substitution. Here's another one. with complete pivoting as opposed to partial pivoting. So with complete pivoting, you find the largest entry in the rows and columns and swap rows and columns. Here, with a banded matrix, which is actually the subject of today, and writing down what are the factors of LU decomposition. So you have PA equals LU. What are P, L, and U? Wednesday, we'll see positive definite matrices. That's a different decomposition called the Cholesky factorization. So how that's to be carried out. Where G is a lower triangular matrix. Here, a condition number of a matrix. So we'll learn about a condition number next Monday, section 3.4. So those are the kind of problems. So since we only have this chapter 3, there's not a whole lot for me to work with in terms of coming up with questions. I would give a midterm later after we've covered more, except February 26th was the ideal day to put it because I'm traveling, and I've learned that I can't really count on a substitute to do what I need them to do in class when it's giving a regular class. But if they're just giving a test, I think they can handle that. Thus it's on the 26th. Okay, so the other part is, so this is part 1. Part 2, what I call lightning round, conceptual questions, and I didn't include it in a practice test because you already have a good resource for that. It's like the concept check questions that you get in Canvas. So really, that's your resource for being prepared for that part of it. Stop that. Okay. I haven't finalized that part yet, but probably about 10 questions or so. So from chapter 3. Okay. So whatever Canvas quizzes you'll have, so we have in Canvas, Sorry, I almost accidentally exposed people's grades. Come on, Canvas. Quit being a... Oh, okay. Okay, so the relevant quizzes, the first 3 that cover chapter 3. I know I have a few from section 3.2. Okay, yeah, so I still have a handful of quizzes to get to, but I also expect to have more quizzes coming in. Wow, that rain's looking awful. Okay, well, we'll see how it's behaving after class. Oh, right. Okay. I'm not going to change a part about regular problems because it was hard enough to come up with the ones that I have. So the number of concept check questions will be different. So, yeah. Sorry, Samson. Okay. All right. But not very different. So, okay. All right. Because yeah, technically the workload is supposed to be different for undergrad versus grad. What I used to do was apply a curve to the undergrad scores, but I was told that that's not the way to go. So, sorry, undergrads. Okay. So be sure to take a look at the practice test. So the last class period before the test. All right, so that. Okay, so Wednesday, February 19th. That'll be a review. So no new material. Will be covering, going over the practice exam solution and just talking about different types of problems and things that you might expect. Okay. But I try to have a no surprises kind of test. Okay. So any questions about that? All right. Now, on to today's actual topic. Okay. So we've been dealing with a general system of equations. So A is n by n. So you always have the option of using Gauss elimination with pivoting. So that's the LU decomposition. And you can then you can always do forward back substitution after that. So that will always work. Okay, so that's like a general purpose algorithm. So any invertible A. Okay, actually, let me change the section here. All right. So the idea is for this week, we're going to look at certain subcategories of invertible matrices and re-examine the whole process of solving Ax equals B for matrices of that type. And see what we can do. That would be, and see what efficiency can be gained in particular. Okay, so today I'm going to talk about banded matrices, and then on Wednesday about symmetric and especially symmetric positive definite matrices. And both of these types of matrices are of importance for certain applications, like solving linear systems and trying to solve differential equations, like partial differential equations especially. Both these classes of matrices, in fact, certain matrices of importance that are both banded and symmetric positive definite, we'll be seeing. Okay, so a banded matrix. Well, I can't type today. Is a matrix for which all non-zero entries occupy a band, if you will, around the main diagonal. So I'm going to define some terms here to make this more concrete. All right, so matrix A has lower bandwidth. I actually want to check my notation to make sure that it is consistent. Okay. All right, so lower bandwidth Q if Aij is equal to 0 whenever I minus j is greater than Q. All right. So if the row is that much greater than the column, then so in other words, the only way an entry below the diagonal can be non-zero is if it's within Q entries of the diagonal. So for example, if Q is 0, then the entry is 0 whenever I is greater than J. So everything below the diagonal will be 0, and the matrix is upper triangular. Now, A has upper bandwidth, P, and I'm putting it above because P comes before Q. If Aij equals 0, whenever J minus I is greater than P. Right. So, okay. Now, the bandwidth, so total bandwidth of A, so this is a number of diagonals with non-zero entries, is P plus Q plus 1. So the 1 comes from a main diagonal, and then we could have, so if it's upper bandwidth P, this is a number of non-zero diagonals above the main diagonal, and this is a number of diagonals below the main diagonal, Q, that may contain non-zero entries. Okay, so finally, we say that A is banded if the bandwidth is less than 2n minus 1. So, because the total number of diagonals is 2n minus 1. You have a main diagonal, then you have n minus 1 diagonals above, and n minus 1 diagonals below. So 2n minus 1 is so that's the most that's the largest of bandwidth can be. So if there's some diagonals that have all 0 entries, then we say it's a banded matrix. Now, really what we care about most are matrices where the bandwidth is not related to n. Like it's just a very small number. So if P and Q are both equal to 1, A is tridiagonal. Because there's a main diagonal, there's a diagonal above, and one below that are non-zero. Everything else 0. Similarly, if P and Q are both equal to 2, A is pentadiagonal. Okay. Other ones of interest that come up. If the lower bandwidth is 0, which would make it upper triangular, but P is equal to 1, is upper bidiagonal. So bidiagonal matrices come up when computing certain matrix factorizations. So you just have a main diagonal and one diagonal above. Similarly, if it's the opposite, Q is 1, P is 0, then it's lower bidiagonal. So these are certain terms that come up. Okay. I want to see if... Okay. So I should really fix the spacing in this matrix, but okay, let me make this bigger. It's kind of hard to tell with the entries being different sizes due to the spacing or minuses or not minuses. So, but this matrix right here, the main diagonal is make it bigger still. -2, 1, 3, 1, -2. So that's the main diagonal. Here we have only one diagonal below that that's non-zero. So the 1, 4, 11, and 3. And then above the main diagonal, we have 1, 8, -2, 1. So that's the first non-zero super diagonal. And then the 5, 4, 7 is a second non-zero super diagonal. So this matrix has upper bandwidth 2, lower bandwidth 1. So the total bandwidth is going to be 4. And sure enough, whatever total bandwidth is, that's how many non-zero entries per row is the most that you can possibly have. Okay. Here's an easier to read example, this one right here. So minus 2 is down a diagonal, 1's above, 1's below. So this is an example of a tridiagonal matrix. So upper bandwidth is 1 because of these 1's here, and then lower bandwidth is 1 because of these 1's down here. This matrix is probably one of the most important matrices you'll ever come across because it is useful for computing approximations of the second derivative of a function. So if I have values of a function evaluated at equally spaced points as a vector, and I multiply this matrix by that vector, and then divide by the spacing squared, that's the result. This matrix times that vector, it approximates the second derivative at those points. So this is used all the time in numerical solution of PDEs. So this is used to approximate like UXX, for instance. Like if you think of the heat equation, UT equals UXX. So this approximates the UXX part. All right. Okay. So tridiagonal matrices like this are very common. Okay. So so what happens when we perform Gaussian elimination? And for now, no pivoting on a banded matrix. Okay. So, well, we go through a regular process, and we eliminate all the entries below the diagonal in the first column, then in the second column, and so forth. Okay. Actually, I think what I'll do... I'm sort of going to carry out an example. But I don't feel like making up numbers. And we don't really care about the numbers anyway. What we care about is which ones are 0 or non-zero. So I'm going to fill in a matrix where I'm going to use x's to signify non-zero entries. Okay, so this is our original A, but I want to make it banded. So I'll give it a upper bandwidth of 2 and a lower bandwidth of 1. So I need to make some 0 entries here. Okay, so need to make a few more entries 0 below the diagonal. Okay, so here's our original matrix, where we have, this is a main diagonal, we have one diagonal below that's non-zero, and then 2 diagonals above. Okay, now, okay, so now what I'll do is, if I'm in the first column, I have this one non-zero entry to eliminate. So the lower bandwidth is 1. So the lower bandwidth indicates how many non-zero entries that are ready to be eliminated. Now, so the thing is, I'm going to take a multiple of this row and subtract it from this row. So I can see here I only have 1 entry, but is that really going to be true for the rest of the way? So let's find out, just to be sure. So, whoops. Okay, so I can eliminate not the 1, 2 entry, but 2, 1 entry. Whoops. Okay, so I'll make a copy. All right, so what will happen is I take some multiple of this first row, subtract it from a second. So that will make this entry 0. But because of the zeros over here, there aren't going to be any new non-zero entries introduced. So that's nice. So our first column is done. Now I move to the second column. Here's a diagonal entry. Again, only one entry below that I need to eliminate. So I'm going to take some multiple of this row and subtract it from this one. And again, it's not going to do any damage, if you will, in terms of introducing new non-zero entries. So, okay, so eliminate A, 3, 2. All right, so okay, so now the row 3, column 2 entry is made 0, and nothing else is messed up. So then I can move to the fourth column, eliminate this entry, and then this entry. So I'll just do those in one shot. So row 4, column 3, and row 5, column 4. That's going to play out the same way. All right, so that one was already gone. And then that one entry in the third column, one entry in the fourth column. The matrix is upper triangular, and notice the bandwidth is still 2. The upper bandwidth is still 2. It was at the beginning, and it still is. So what we can say is, in each column, only need to eliminate Q entries, whatever the lower bandwidth is. So as a result of that, in this case, we only had one multiplier per column. So in the LU decomposition, L, which is a unit lower triangular matrix, has lower bandwidth Q. So the bandwidth of L matches the bandwidth of the original matrix of A. Also, if we look at these row operations, like going from here to here, this diagonal entry was used to eliminate the one below the diagonal. These two entries are used to modify these. But this one, not touched, because the entry above it is outside the band. So, in other words, only this entry is made 0. These entries are the ones that changed from the row operation. How many entries is that? Equal to the upper bandwidth. So each row operation only affects P entries. That's the upper bandwidth. So U has upper bandwidth P. All right. So the bandwidth propagates to the LU factors. Now, so what's the total amount of work that we have here from doing all this? So all right, so in other words, total number of flops. Well, we have n-1 columns to work on. At most, P entries to eliminate per column. So in other words, the total number of row operations is order n times P. I notice I say order of that. I'm not being precise about every single term. All right, but so order NP, row operations. But how much work does each row operation? Sorry, that's not P, that's Q. Lower bandwidth, how many entries you eliminate per column. So order NQ row operations. So order NQ row operations, each costing P flops, because each row operation affects P entries due to the upper bandwidth. So total work is order NPQ. Now, this is consistent with Gauss elimination on a general matrix, because in a general matrix, you have order n entries to eliminate in each column. Each row operation costs order n flops, because usually you're working on the entire row from a diagonal on. So, in a general case, the total work would be n, so order n cubed. But if P and Q are independent of n, like a constant bandwidth, for example, a tridiagonal matrix where P and Q are both 1, then having a matrix be banded eliminates 2 orders of magnitude from a total work. So an algorithm that seems quite expensive, Gauss elimination in general, order n cubed operations, now takes order n. So it becomes a much faster process. Okay. Now, I think I may have given. Let's see which problems I assigned for this section. Okay, 1, 3, 4, 7, 8, 12. Okay. Okay, so I've discussed some of the homework problems, but oh well, it happens a lot. Okay. Now, I want to focus on one case of particular interest. So, for a tridiagonal matrix, so P and Q are both equal to 1. Right. Because if you know if a matrix coming in is banded, you don't want to use a full Gauss elimination algorithm. That'd be wasteful. But what you can do is take into account the bandwidth to avoid working with entries that you know or already know are going to be 0. Okay. Now, so what I'm going to do is I want to take the actual algorithms, like as stated in the book, for forward, back substitution, and also Gauss elimination, and trim those down for the case of a tridiagonal matrix. So you can see what's done to simplify. Now, I don't want to take the time to type out those algorithms, because that'd be kind of useless time for you. So I'm going to go into the LaTeX files for a book that I have here and copy them into my notes. Since the notes are LaTeX also. Okay, so I just need to find... Okay, so for instance, here's the back substitution algorithm. Okay. Alright, so there's 3 algorithms to look at. So first there's Gaussian elimination. Okay, and then forward substitution, and then back substitution. All right, so I'll just paste back substitution 1 right here. Okay, and then I need to also dig up the ones for Gauss elimination. Okay, here's Gauss elimination. All right, and then forward substitution. Okay, here that is. Okay. So this is for a case of a general n by n matrix where any entry can be non-zero. So now we'll take into account the bandwidth. So first for Gauss elimination, we are still going to look at every column. So this outermost loop is not going to change. But here, in any column, in whatever column J we're in, okay. So whatever column J I'm in, I only have to eliminate the entry right below it, which is in row J plus 1. So in other words, I will only be equal to J plus 1. So, so in here, I'll set I equal to J plus 1. Also, I don't need the loop anymore. So this second loop, I'm just going to comment that out. Okay. Actually, I'll also unindent. Okay. Okay, so anywhere I see I, I'll just do J plus 1. Okay, and actually, this is for LU decomposition, so I'm not going to bother with the right-hand side anyway. Okay, so one loop has been done away with. Okay. Now, here we do the row operation. Now, here we're doing it working with columns J plus 1 to the end in a general case. Now, but the thing is, AJK is the element you're fetching from row J. Now, if K is equal to J plus 1, then we will have a non-zero entry in that row, in that position, because it's on the super diagonal, so the entry's above. But if K is greater than J plus 2, that means the row and column indices differ by more than 1. Those entries are 0 in a tridiagonal matrix. So K is only equal to J plus 1. So in other words, there's no point having a loop there either. So I'm just going to fill in K equal to J plus 1. And this loop is gone. Okay. And I can unindent this. So that's it. Gauss elimination is reduced to practically nothing. So we just compute this multiplier, perform this row operation that affects only one element. So this entry is being affected by the one right above it. And that's it. Okay. All right, so that's how Gauss elimination is transformed. So only n-1 iterations altogether, each one carrying out 1, 2, 3 flops. Okay. So questions about how Gauss elimination was simplified in the case of a tridiagonal matrix. All right. Now, so forward substitution, it's the same idea that here the row and column indices can only differ by at most 1. Now, j is going from 1 up to I minus 1. Well, j can only be equal to I minus 1 to actually do anything, because otherwise the row and the column indices would differ by more than 1, and therefore Lij would be 0. So I'm going to set j equal to I minus 1 in here. Okay. So this loop can go away. And I'll unindent this. So in fact, I don't even need this line, y equals bi, and then I update y. I could just put the b down here. So that's it for forward substitution. Again, one loop that computes these n elements. And back substitution is going to be similar. Because here, j starts at I plus 1 and goes up to n. But once they get to I plus 2 and beyond, uij will be 0, because u has an upper bandwidth of 1. So remember, bandwidth is about what is the maximum difference between the row and column indices to have a non-zero entry. So in back substitution, I will set j equal to I plus 1. So that loop is gone. And here too, I don't need this line that just sets x equal to y, the right-hand side. I can just put that down here because there's no more loop. Okay. And then we just have this one division here. So that's it. That's all the algorithm is reduced to when the matrix is tridiagonal. But we're actually not done in transforming these algorithms, because there's another thing to think about. Now, we have gotten a job done in terms of cutting out unnecessary floating point arithmetic operations. So these operations have a desired efficiency in terms of arithmetic, but there's another inefficiency that we have to deal with. Now, so banded matrices should not be stored as a 2D array, or as 2D arrays. Okay. Now, why? Because there are certain entries that are 0 the whole way through the process, and we're just gobbling up memory with a bunch of zeros. Okay. Instead, we can store them as vectors, one per diagonal. So, back to this same example of tridiagonal case, we use a vector L for the subdiagonal, because the LU factors, UI for the superdiagonal, so the entries above, and DI for main diagonal. So now what I can do is go back to these algorithms and take a vector storage into account based on whatever indices we have here. So for example, AJJ, that's the jth entry of the main diagonal. So that would just be DJ. So wherever I see a diagonal entry, I'll just go ahead and change that. Actually, you know what? I'm not going to do it right here. I'm going to make copies just so you can see both in the notes if you look at them later. Okay. Okay. So, in all three algorithms, wherever I see a diagonal entry, I'll refer to it using a vector D. And without one index, okay. All right, so that's the easiest change to make. Okay. Let's see, and also in back substitution, we have a diagonal entry there. Okay. Now, back to Gauss elimination. The multiplier is a entry from the, goes in the lower triangle. That's where it's stored. And now here I have a choice. Do I use a row index or a column index? I'm going to use the column index for referring to subdiagonal entries because for when you're below the diagonal, the first entry is in column 1. So because it starts at 1, I'm going to use J. All right, so any subdiagonal entry, I'll use the column index. So that's going to be LJ. I want to check something here. Okay. Oh, actually, up here, this therefore should also have been J plus 1. Okay. So since the multipliers go down there, I'll put those in L. Okay, so LJ over DJ, and then here, too, I have LJ. And then here, AJ plus 1, that refers to a super diagonal entry. For those, I'm going to use a row index, because when you have a diagonal above a main diagonal, the first element is going to be in row 1. So that would be UJ. Okay. Wait. I just changed the wrong thing, didn't I? Okay. Okay, right here. UJ. Sorry, now I have to go back and fix some things. Because I was changing the wrong algorithm. Okay. All right, so right here, this is Gaussian elimination when for using vector storage. So it fills in the entries of the lower triangle just by dividing by the diagonal entry, changes the diagonal because that's what's effective of a row operation. Notice that the upper vector for the upper diagonal, the super diagonal U, it's used, but it's never changed. Just because that's what happens with Gaussian elimination on the banded matrix. Okay, forward substitution, again with vector storage. So I'm just going to use the column index here. I changed the wrong thing again. Sorry. Okay. All right, so right here I use that entry from vector L. Okay. And then in back substitution, here I just need to use a row index. And then everything else is set. Okay. This one. Okay. Now, the only thing that I have to be more careful about in these implementations, like right here, when I is equal to 1, this reference would be invalid, L0, because the elements of a vector L start being indexed at 1. So here, what I really should have is like an if statement. Or what I could do is the following. Set y, or, okay. All right, so if I could set y1 equal to b1, and then for I going from 2 to n, I'll do this. So that's a more careful implementation to avoid any invalid references. Same thing down here for back substitution. The first equation I use is the last equation, equation number n. And in that case, I wouldn't have a step like this because I don't have an xn plus 1. I'll only have a division. So for back substitution, I should begin with xn is equal to yn over dn. And then I start with, and then my loop starts from row n minus 1 down to the beginning, and then everything in here will be valid. So I have to be careful about that in forward back substitution. But otherwise, everything else is good. So now it's the matrix is represented as these three vectors: one for the main diagonal, one for the super diagonal, one for subdiagonal. So then there's no need for two-dimensional array storage. There's nowhere in here any of these algorithms that uses two indices, just indexing into a vector. So questions about how these algorithms were transformed from the original into what we see here. Wow, it's like monsoon out there. Okay. All right, so that's what? All right. Now, okay. There's one problem with Gauss elimination on a banded matrix, and that's with pivoting. Because pivoting is just as necessary for a banded matrix as for a general matrix. Okay. So as an example, I'll just create one in MATLAB. Oh, need to make this a lot bigger. Oh, well, I'm in the folder for Chandler's homework right now. Okay, all right. Let's go up a few levels. Okay. Oh, actually, I don't want to be in that folder either. Okay, but I still need to make this bigger. All right. So let's make a random matrix. Oh, wait. Okay. I might be able to see the whole matrix at once. Okay, so now I can see everything. Now I want to make it banded. So first I'll take the lower triangle. Okay. So diagonal. Okay, so that keeps the upper bandwidth of 2. And then I'll use lower bandwidth of 1. Okay. So now we have a banded matrix, lower bandwidth 1, upper bandwidth 2. Now, if I were to do Gauss elimination of partial pivoting, now in the first column, no need to pivot. So what I can do is, all right, so row 2 is equal to itself minus multiplier, which would be A21 divided by A11 times A row 1. So, all right, so that's a first row operation. Now we get to the second column. I need to look at these two entries, the 332, this one and this one. Whichever one is the largest has to get swapped into the diagonal position. So this one is not the largest, so I need to swap rows 2 and 3. So row 2 and 3, all columns, is equal to row 3 and 2, all columns. So now rows 2 and 3 are swapped, and look, we have an entry outside the band. So that's okay, things are only going to get worse. So I'll do another row operation. So row 3 is equal to itself minus row A32 over A22 times row 2. Okay. And yeah, so now we have these two entries that lie outside the band. And then I need to, here, third column, no need to pivot, because we've done enough damage as it is. Okay, and finally down here, I need to swap rows 4 and 5. Okay, and then do one last row operation. Okay, so now it's upper triangular at least. And L will still have a lower bandwidth of, actually, I'm not even sure about that. Okay, but the point is the matrix is no longer banded. And actually, I think L will not have lower bandwidth 1, because even though I only had to eliminate one non-zero entry per column because of the swapping, L would not have a right lower bandwidth either, or a desired lower bandwidth either. So, to what is called fill-in. So that's the introduction of non-zero entries outside the band. So then you lose the efficiency that Gauss elimination on a banded matrix is supposed to give you. So it just wrecks everything. So what can you do about it? Because the need for pivoting has not gone away. So can try other pivoting strategies, such as requiring that the multipliers in absolute value less than or equal to some threshold L instead of 1, which is what partial or complete pivoting would give you. So if you pivot a little more flexibly, maybe you can at least preserve sparsity to an extent. So there's things like that can be done to at least lessen the damage. But it's a big problem with the banded matrices is preserving that sparsity, preserving the efficiency gain that you get because there's so many non-zero entries to begin with. Okay, so it's quite a mixed bag. That you have a great efficiency gain unless unless you're pivoting. Yeah. Okay. So in the last 12 minutes that we have, do we have any questions about either this or homework 2 that's coming up due pretty soon?
Have you posted homework notes?
Shoot, I forgot to do that. Okay. Well, I've just been reminded. Oh, you know what? Okay. As a very quick stopgap, okay. Okay. Those are hints from 2018. They should still be valid. The only reason I didn't post these, I want to look at them to make sure. But I will. So at least you have something, and then I'll take a look at those. And if there's any changes to make, like the date, then I will. Okay. Sorry about that. I gotta remember to do that for the other assignments too. Other questions?
So I have a question about the uniqueness of the energy decomposition.
Okay.
Because we are using the energy decomposition in this text talk about having L as unique lower triangle.
Yeah.
What if L wasn't unique lower triangle? Say maybe U was unique lower upper triangle.
Oh. Okay. So L was not unit.
Yeah.
But
U is unit.
Okay. Well, so if you require U to be unit, I think a proof would play out the same way. But it's still going to be unique. Or really, if I could be more general, you could think of it like if you make a imposition on one of the diagonals, because what happens in a proof is you have this equation where you have a lower triangular matrix on one side, upper triangular matrix on the other. Therefore, they must both be diagonal. And the only reason we get uniqueness is because on one side, you end up having all the diagonal entries must be 1, because of either the lower being unit, which would be the same thing if the upper was unit. If you don't require either one of them to be unit, then it's no longer unique. So what you have is, on both sides, you still have a diagonal matrix, but that diagonal matrix is not necessarily identity, because if you've lost that assumption of one of the factors having to be unit.
So if we do not impose, or let's say I choose to impose on U,
Yeah.
and someone imposes on L, our factorization is different.
Okay, that factorization, like if you make U be unit upper triangular, that factorization would be different from the traditional LU, but it would be the only factorization of that kind.
The reason why I'm saying is when I learned energy decomposition as an undergrad, we imposed that U be units.
Interesting. Well, actually, I could see that. I guess like kind of like a reduced row echelon form or something.
Yeah.
Okay. Yeah.
So here we are having L to be.
Yeah.
I'm kind of used to working with.
Yeah, and I guess in typical first linear algebra courses, you have a scale of the rows so that of a row echelon form so that the diagonal entries are 1, and yeah, okay. So leave it to those numerical analysts to go rogue and try something different. So. Oh, yes? Oh, sorry, do you have a question?
Oh no, I just popped myself and it hurt.
Oh, yeah, ow. Okay, okay. Just hearing about that is, okay. Other questions?
Okay, 3, 2, 4.
3, 2, 4. Okay. Okay.
So when doing this proof, are we using, say, maybe 30 by 30 matrix to show the proof or in general?
Okay. I do want to see a general argument. Now, okay. So, although if you work it out for a small case like 3, you kind of see how it's going to go. Now I'm not looking for some rigorous like induction proof or something, but I don't want to like limit it to a specific dimension either. Because how you go about it comes from the general formulas for like for matrix multiplication. And yeah, so it seems to be general in that case. So I'll give decent partial credit for one that's specific, but I tend to be pretty generous with partial credit anyway. Unlike some faculty here. But all right. Any other? Well, and I seem to have. Well, I'll find out if I take a moment disk space when I try to save this thing. But okay. So homework due Wednesday. But you know how I am about due dates, most of you. Be sure to bring your questions if necessary. Okay, you may scram.